Hi everyone, this is just a quick video to bring some of the three-dimensional images that are in the textbook to life. Some of the direction fields, we have static pictures in the text and it's difficult to really tell what's going on. So this is just an opportunity for us to take a look at the vector fields and move them around a little bit and hopefully give you some more insight and intuition as to what's happening with these systems of differential equations. So I'm going to start. I'm here in the text. I don't expect you to be able to read this. This is just a point of reference for you, and I'm in section 9 and looking at these two images here. So what I want to do first of all is take a look at this image of the direction field that's a little bit grayed out. So we have the red vector here, which is simply representing the fact that every point in the three-dimensional space of HVT has its rate of change associated with it. This is actually a zoomed in picture. Let me zoom out and we can see the entire vector field, similar to the blue vector field we have over here. And now let me just show you what this actually looks like as we move it around. So we can see that there's a lot of symmetry to what's happening with the vector field. And when I look straight on along any one of the t values, I can see that the vector field actually looks the same. So for example, if I look down the h-axis and I look at the vt plane, what I see is I see that for every value of t, the vectors look exactly the same. But of course, these are not exactly what the vectors look like. Those are just projections from the three-dimensional field that we can see here. So we can take a little bit deeper look at this when we look at the solution. And this gives us some insight into what the solution for a system of differential equations really is. The solution's in magenta with the initial condition down here as the blue dot. Of course, it's in the direction field. And what that means is the solution has to be tangent to any of these vectors. Let me zoom in and demonstrate. Here's a vector right here. This is actually the red vector in the previous image. And you can see that the solution is tangent to that vector. So at the point -1, 0, 2 pi, we have to be following in a direction that is exactly tangent to that vector. And this is the information that's provided by the direction field, the same as it was when we had just a single ODE. Let me zoom back out then. So when we look, for example, along the VT plane, so we're looking down the h-axis here, this is the VT plane, and these pictures are in the text as well. This is the two-dimensional sinusoid that we see for v as a function of t. I just want you to know that the solution is not a set of two separate functions. It's a single function which is drawing this parametric curve in three-dimensional space. It's just when we look at it from the perspective of v or h, those are different functions that need to be combined into a parametric curve for us to actually see the entire solution here. So the solution is not separate curves, it's just a single space curve. Before we continue on, I want to go back and take a look at some of the stuff that you did with phase lines with a single ODE. All right, I've pulled up page 29 of the text here where we're looking at the differential equation y prime is equal to y squared minus 1. And here's the direction field. I've replicated that direction field here. It looks the same, but it's actually been done in a three-dimensional graphic, so I can show you what's actually happening when we come up with our phase line. So what we're doing is, because every column of t values here, rates of change, is identical, we're going to compress. So we're going to come out here and we're going to compress all of this information down. And I know you've seen this already, but let me show you the graphic on what this actually looks like. So we're compressing down here in the t direction, and what we end up with is an image that looks just like the phase line. We can see that the solutions, and this is the projection of those vectors onto the y-axis. And we can see here that we have rates of change going up towards -1, and then between 1 and -1, y values, the solution's decreasing down towards -1. And then of course up here those solutions are increasing. So this three-dimensional picture is really the same as what we get with the phase line when we condense down in the t direction. And that's what we're doing. We're just smashing our view down in the t direction to only consider the dependent function y. Let me show you one more time as we rotate this in. So we rotate this in and we see all of the symmetry that's there because it's an autonomous equation, but then we come down and we end up with something that looks very much just like the phase line. The reason I want to show you this is because we have the exact analogy when we're looking at items in 3 dimensions. Let me pull this image back up. So here's our solution again, this time for the system, and we have our 3-dimensional direction field. But as we noted, and this is in the text, for each value of t, everything is exactly the same. So we are going to compress, in this case we're going to compress down in t, and what we're going to do is go from having a phase line to a phase plane, and as we do that, we end up with the image that looks like this. And the reason I want to show you this again is the fact that for the 3-dimensional picture, it helps, I think, to see we really have a 3-dimensional space curve. We have a full direction field in 3 dimensions, but we are compressing the t direction to come up with a phase plane. And this phase plane image here is analogous to the phase line. It's just now we have 2 dependent functions instead of just 1 dependent function. The last thing I want you to note is the incredible increase in complexity of what we can have happening in the phase plane versus the phase line. For a phase line, things are really boring. We either have equilibrium solutions or we have solutions that are increasing or decreasing. There is no possibility, for example, between the -1 and 1 equilibrium solutions for the solution to bounce back and forth. That's never going to happen. When we have a phase plane, now we've included a second dimension and things are far more complicated. We can have, as we see here, this is a limit cycle or a trajectory that is circular, even though we know that it's actually spiraling. But from the context and the perspective of the phase plane, this is a 2-dimensional curve in the HV plane. We can have all kinds of different curves inside of the plane. The next video, what I want to do is show you what happens when we add a 3rd dimension to our phase space. So we'll go from phase line to phase plane to 3-dimensional phase space, where the complexity of the things that can be considered increases yet again. Thanks very much.